All right, so this one-to-one and onto come from unit or section two, and that's covered in a previous course for your math path at Thomas University. So what we're going to look at here is just like a quick little review because this pops up inside of these definitions, and so to be able to move forward, you need to kind of like be able to identify one-to-one and onto. All right, so one-to-one, if we read the definition, we'll call this set A, we'll call this set B. That means that this is the input and this is the output. And so in this case here, this is a one-to-one function because no element of B has more than one arrow pointing to it. So like for example, this element of B comes from one thing over here. This element comes from one thing, and this element comes from one thing. So this is an example of a one-to-one. If you take a look at this example, this is not one-to-one because this guy right here, this element goes to three different inputs. This output goes to three different things or comes from three different things. So this is not one-to-one for that particular case. So this is not one-to-one there. So let's take a look at onto. Onto, by definition, would be A to B, function A to B is called onto B if every element of B has an output from an input of A. Sorry about that. So like for example, this would not be, the first one would not be onto because this is B and this is A and this is my input and this is my output. And so in this case right here, we have 2 goes to 1 and 3 goes to 1 and 5 goes to 1. However, in order to be onto, even 1 would need to go to 1. So 1 could need to go to someplace. So to make this onto, I could just make that one go there or make it go to some other place. And then every element of B would be onto an element of A, and that would be an onto function. All right, same thing here. This is also not onto because we have 2, 3, 4, and 5 that do not go onto an element of A. So kind of tricky. So I think the best way to always look at this is to go from your output back to your input and then kind of look at the definition. So if you're one-to-one, then you're going to one element over here in the input. If you're onto, then every element of the output has to go onto something. It doesn't matter if they're repeated. So like if I did 3, 3, 3, 3, 3, or sorry, I went to 2. But like if everything over here went to one of these, that would be onto. But that doesn't happen, so that's why it's not. All right, so onto and one-to-one come into play because of the definition of what we say is called isomorphic. And in geometry, we say that two figures are congruent when they have same size and shape. In graph theory, two graphs that share all essential properties are said to be isomorphic. So kind of leading into that, so traditionally we say two things are congruent if they have the same size and shape. But when we're looking at if we're looking at like vertex edge graphs or graphs in this route, when we have that essentially all the same properties called isomorphic. And so to be isomorphic, we have 3 requirements. So the first requirement is that vertex 1 to vertex 2. So there's some connection between vertex 1 and vertex 2. And then from vertex 1 to vertex 2 is 1-to-1 if it does not send 2 distinct inputs to the same output. So just reviewing, so don't get confused by that. So 1-to-1 is you go from that output gives you one unique input. And then onto if every element of the list of vertices in V2 is an output from something from V1. All right, so then we have this definition. Let's see. So 2 simple graphs, graph 1 with vertices and edges in it, and graph 2 with a certain number of vertices and edges in it, are isomorphic, meaning that they have essentially the same properties. So traditional geometry, we call that congruent, provided that there is a 1-to-1 function for all vertices, u to v, and they in G1 are adjacent if and only if FU and FV are adjacent vertices, and this is called isomorphism. All right, so let's take a look at some examples. In short, an isomorphism is a one-to-one onto function between vertex sets so that the function preserves the adjacency relationship in both graphs. So remember, adjacency is the idea that P and Q are adjacent. All right, so let's take a look at this. So show that two graphs in figure 5 are isomorphic by finding an isomorphism of vertices G1 and G2. All right, so in this particular case, what we're saying is if we look at one-to-one, so we have, sorry, I tried to write with my pen. Oh, on the wrong thing. All right, so we start this guy off and we see that P goes to Q. Let me hit pause for a second. All right, so to be able to see that what this mapping is to show this isomorphism, what I've done for myself is I've kind of thought about like what connects. So like for example, if I'm trying to figure out like who P would be inside of graph 2, I kind of laid out to kind of say, okay, so I know P goes to Q and I know P goes to R. And so when I'm looking over here, I'm trying to look to see like a similar situation of a vertex that goes to two separate people. So since we have the answer here, we can kind of cheat and see that A goes to B and A goes to C. So therefore, what that's saying is that in this case right here, we have a one-to-one function that P goes to A. All right, and so we're going to look at that function of that one-to-one. So P and A are essentially the same point. And then from there, we can then decipher that Q, in this case, would be our B. And that's because we have P goes to Q and A goes to C. So that means that Q and I'm sorry. So I did that order. So P goes to Q and A goes to B, so Q goes to B in this particular situation. All right, so taking a look at moving down the list, let's go to R. So they're saying R goes to C. Well, that's because P goes to R, and then A goes to C right there. So P goes to R, A goes to C, and so that gives that relationship of R and C. All right, and then from there we have Q going to R. So we have Q going down to R, and so now we know that Q is B, and so we've already got the Q to B. Sorry about that. All right, next one is that we have S is D, and that's because of this situation right here. So we have R goes to S, and C goes to D. And since R goes to S and C goes to D, that means that S would go to D. So S and D are my my one-to-one relationships here. So S goes to D. And then last but not least, we have R goes to T. And so if R goes to T, then that means that we would have C going to E. And so we have a connection between T and E in this particular case. So what we're essentially saying here is what we've worked through or tried to work through is, let me get my eraser, is what we tried to point out here in this particular case is that point P, oops, sorry about that, is that point P is essentially point A. They're one-to-one. And point Q is essentially point B. They're one-to-one. And point C is essentially point R. They're one-to-one. And point S is point D. They're one-to-one. And then point T is point E. They're one-to-one. So we have a one-to-one relationship because every one of the points in graph 1 goes with a point in graph 2, or vice versa. Every point in graph 2 has a corresponding point in graph 1. And they're onto for the same reason because every point in graph 2 comes from at least one point over here. So these are isomorphic graphs. They're essentially equal to each other. All right, then we have one last little thing to take a look at here. Hit pause and kind of get myself ready to go. verbally. This slide is basically just an explanation of what I just walked through in that previous example to show that the isomorphism. And so they show you how instead of like digging through with like arrows like I did, they actually go through here and create a table. And so they're like kind of like talking about adjacency to be able to see the adjacency pairs there. And that's kind of what I was doing to show that P is the A and Q is the B, as I was showing the relationships going down. So I was showing like how P went to Q, so therefore A would go to B, and then Q went to R, so B would go to C, and so forth. And so we could start to then see that the relationships going horizontally came from the relationships going vertically. All right, so hopefully that helps you get through isomorphism. You have some practice problems, just kind of dig into these. On this particular section, we're really not solving any proofs. We're just identifying and using the definitions of isomorphic, simple, and compound to be able to determine whether or not examples are meeting those requirements.